Hey guys, Miss Peterson here, and welcome to our lecture on universal gravitation. Here we're going to be talking about Newton's law of universal gravitation and doing some example problems. So we'll go ahead and get yourself set up to write notes. Make sure you have a paper and you're ready to go. So what is Newton's law of universal gravitation? Basically, it explains the gravitational force between any two objects with mass. The equation that we talked about before was only for the force of gravity of something being attracted to the Earth. So Earth was one of these masses. But this can be done with any two masses. This could be the Earth and the Moon, two students sitting in class, a star and another star, a star and a black hole. Any two objects, this equation can calculate the force of gravity between them. Okay, this is one of those fundamental forces of the universe. Now, it has this G in here. That G is the universal gravitation constant. The number value of it is 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. And I'll show you why those units are weird when we do our first example problem. But those are the basic units for it. Now, is that constant a big number or a small number? And what does that mean for the force of gravity? Is the force of gravity a really strong force? I mean, it feels strong to us. It's one of our most important forces. But also, I can overcome gravity all the time. Okay, the Earth is pulling on my body right now, and if I wanted it to not be, I could just jump, okay? And I can fight gravity. So even though, yes, gravity is a strong force and it impacts our lives daily, in terms of magnitude, it's not that strong, okay? We can fight gravity. We do that when we learn to walk. Yeah. Okay, cool? Okay, cool. Now, what often comes up in this conversation is what is the difference between G, the universal gravitation constant, 6.67 times 10 to the negative 11, and little g, the gravitational acceleration on Earth, which is 9.8 meters per second squared. And I'm going to actually show you guys with an example problem. So we're going to calculate the force of attraction between the Earth, which has a mass of 5.98 times 10 to the 24th kilograms, and a physics student of unknown mass m. So we're going to be finding this force in terms of m. That's still going to be part of our equation. And the student standing at sea level, which is a distance of 6.38 times 10 to the 6 meters from Earth's surface. That's the radius of the Earth. So we're going to plug it in. Remember, our equation is force of gravity equals G times m1 times m2 over r squared. So let's go ahead and plug in those numbers. Okay. So first we have the force of gravity equals G, which is 6.67 times 10 to the negative 11. We're not going to worry about the units for right now. Times m1, I'm going to call m1 Earth. Okay, so that'll be the 5.98 times 10 to the 24th kilograms. And then we're going to leave the second mass just as m. All over that distance, 6.38 times 10 to the 6th meters squared. So basically, when I calculate this right now, I'm really only calculating this part of the equation, this g m over r squared. Okay, so I'm going to plug that into my calculator. 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24th divided by that radius, 6.38 times 10 to the 6th squared. And when I do that, I get 9.799, aka 9.8 times m. Does that equation look familiar? Yeah, okay. We can use the force of gravity to determine the gravitational acceleration or force of gravity of anything on Earth. The 9.8 that we use is just a shortcut for it. Okay, cool? Okay, cool. Let's go ahead and look at another example problem. Okay, so what is the force of attraction between Earth, mass of Earth, and a 2.08 times 10 to the 4th kilogram Model 5B rocket launcher? This is the rocket launcher that was accidentally launched into space during a recent rocket launch, and it, of course, didn't get launched completely to orbit, but pretty close to a near-Earth orbit. And because it wasn't far enough, it's not designed to stay in orbit, it ended up crashing into Earth. And why? Because there was a force of attraction between it and Earth. And how big was that force? That's what we're going to find. So we know that we're going to be using Newton's law of universal gravitation, where we have the mass of the Earth, and I'm going to use R for the mass of the rocket, over the distance between them squared. Let's go ahead and list out and label our variables. G is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. Mass of the Earth is 5.98 times 10 to the 24th kilograms. The mass of the rocket was 2.08 times 10 to the 4th kilograms, and the distance between them is 6.46 times 10 to the 6th meters. Now, just a little note about when we're doing problems like this. Whenever we're doing problems using this, it's measured from center of mass to center of mass, that distance. So it's not just distance away from Earth, it's like distance from the center of Earth. So just kind of keep that in mind. Let's go ahead and plug in our numbers. So we have that the force of gravity is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared times the mass of the Earth, 5.98 times 10 to the 24th kilograms times the mass of the rocket, 2.08 times 10 to the 4th kilograms, so about 20,000 kilograms, divided by the distance between them, 6.46 times 10 to the 6th meters squared. Okay, now this is a lot of big numbers and a lot of scientific notation. Make sure you can plug scientific notation into your calculator. Okay, what I often do is I plug in the bottom first, okay, because that's the squared one. So times 10 to the 6th squared. And when we do that, we get, I'm just going to do this like off to the side in a different color. We'll do red. That comes out to 4.17 times 10 to the 13th meters squared. I can also show you how those units work out. We have kilogram and kilogram, cancels out that kilogram squared. Meter squared here, cancels out with meter squared there, and we're left with newtons. Okay, so let's go ahead and plug it in. I recommend putting the whole top in parentheses, okay, and then divide it by that bottom number. Times 2.08 times to the 4th, okay, divided by 4.17 times 10 to the 13th. And I got a force of gravity equal to 19.9 times 10 to the 5th newtons. So pretty strong force of gravitational attraction there. Let me double check my calculation because I feel like it's a little bit high. I'm wondering if I make sure I have that negative 11 on my universal gravitation constant. Oh, and that time I got an error. Why am I getting oh, because I forgot to do that. Okay. Double checking this on my calculator again. Okay. Times 10 to the negative 11 times 5.98 times 10 to the 24 times 2.08 times 10 to the 4th divided by 6 actually do that, like 6.46 times 10 to the 6th squared. Okay, yep, got the same answer. So we're good to go. Okay, cool. Okay, cool. Let's look at another example. So this is a more challenging example. We're going to be putting together universal gravitation with centripetal force. This problem asks, how fast will the satellite with a mass of 2,030 kilograms need to move in order to maintain an orbit at a height of 20,000 kilometers above Earth's surface? And we are given the radius of the Earth and the mass of the Earth. Okay, so let's just kind of conceptually think this out real quick. I have Earth, okay, and then we are going to have a satellite up here on Earth. Okay, there's my satellite. That's what it looks like, sure. And it is at a height of 20,000 kilometers. Okay, this is definitely a challenging problem. But first, let's just think about it, okay? Because we'll probably be able to make this a little bit easier. That force that keeps it in orbit is the centripetal force, okay? So we can say that the centripetal force will equal the force of gravity between those objects, okay? If those two forces are equal, then it will stay in that perfect orbit, okay? So far, so good. So let's go ahead and see if we can figure out what speed that would need and talk about what things we have going on over here. Well, we know for centripetal force, it is the mass of the orbiting body. I'm going to call that the satellite, okay, so ms for satellite, okay, times the velocity of it squared, and that's what we're trying to find here, divided by the distance. Again, just using the equation for centripetal force, mv squared over r. And that's going to equal the force between two objects, so capital G, mass of the satellite times the mass of the Earth divided by the distance between them squared. Okay, so some things are the same on both sides of the equation, so we can cancel those out. For example, the mass of the satellite doesn't matter. And this makes sense. Why? Well, if you think about it, every time we send an astronaut up to the International Space Station, we don't have to change its speed or change its orbital radius or anything like that for it to maintain its orbit. The mass of the orbiting body doesn't matter. All that matters is the mass of the bigger object that is attracting it, okay? The mass of the Earth. That's what determines the force between them. So we can cross out this mass of the satellite, okay? One of these distances can cancel out with this distance, so we'll just have r there. So we end up with the velocity of it squared equals m times the mass of Earth divided by the distance between them. To actually get the velocity, then, we just take the square root of both sides, okay? So we're just about there. Only thing that we need to talk about is what this distance actually is, okay? Oh, and I forgot G. Can't forget G, capital G, times the mass of the Earth. This is actually one of Kepler's laws that we'll be learning about next week. So if Earth has a radius of this much, and then we have 20,000 kilometers, I'm going to go ahead and convert the 20,000 kilometers to meters. So 1 kilometer is 1,000 meters. So when you plug this into your calculator, you get, I'm going to go ahead and put it in scientific notation mode, 2 times 10 to the 7th meters. Okay, so 2 times 10 to the 7th meters. And we will have to add that to the radius of the Earth in order to get that actual distance. Okay, so I'm going to add that to 6.38 times 10 to the 6th to get my actual distance, which is 2.64 times 10 to the 7th meters. Okay, And again, the reason that I had to add that is because we measure from center to sensor, and this was just the height above our surface, which is not the same as the distance between those two objects. So let's go ahead and plug in our numbers. Square root of 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared times that mass of the Earth, 5.98 times 10 to the 24th kilograms, divided by that distance that we just calculated, 2.64 times 10 to the 7th meters. Okay, meter cancels out the squared, squared cancels out that one, and we are left with nothing to cancel out the newtons. Oh, but newtons are weird units too. Newtons are actually kilogram meters per second squared. So it does end up working out. 5.98 times 10 to the 24th divided by 2.64 times 10 to the 7th, and then we take the square root of that, and we get a velocity of 3,887 meters per second. So about 3,900 meters per second. Does that seem reasonable? When in doubt, ask Google. What's the average speed of a satellite? Average. We'll be even more specific, orbital velocity of a satellite. And we get the International Space Station is 7,000, but the satellite orbiting Earth is about 3,200 meters per second. So 3,800 meters per second is definitely reasonable. And that's it for this lecture. Okay, cool? Okay, cool.